So today I'll be discussing about two important models where anyone who is trying to propose something or trying to work on a data set, how they can process this data, or what are the important terminologies that has to be covered, you know. So especially with respect to the statistical data that will be generated by both SIoT and IIoT. To begin with, I'll start with the fundamentals of what is statistical data, and then I'll move on to the ontological model. Finally I'll end up this by presenting just executing few commands or a few methods where how to analyze the results, Okay. So what basically the statistic is, it's a mathematical science that is concerned with the collection of the collections, analysis, interpretation or explanation, and also the presentation of data. Right? So if you look into this SIoT based data generation things, there are n number of sensors here, like temperature sensors, you have a sampler, you have an actuator, there is something like social account, or somewhere you have a set of persons involved in this, okay, or some property, there is some lightning sensors or a location sensor, right? Now these data will generate a different set of categories of data, in fact. Now, when I want to perform some analysis on these data, like how this data can be utilized to take some actions, So statistical way of methods or the models will help us to understand these data, and also it tries to measure these data. Okay. So the fundamental things that are required for statistical analysis is based on the organizing and collecting data through a graphical display and numerical summaries. So when you say graphical display or a numerical summary, two kinds of data. One is categorical data and another is quantitative or a numerical data, right? So under further the data, when you say categorical data, it can be a nominal or it could be an ordinal, or when you say numerical data, it could be based on the intervals or based on the ratios. Okay. Now these data can be measured or summarized like medians, quartiles, means, weighted means, trimmed means, standard deviation, correlations, or regression lines. Now, looking at each thing, what is a median, right? A median value can be, it's a value of a range of values, right? And quartiles are the number of data points, which basically divides into 4 parts, or the 4 quarters, or more or than less equal size. Okay, but for this the data must be ordered from smallest to largest to compute the quartiles, and mean, and it's an average or an arithmetic average, which is a central value of a finite set of numbers. And weighted means, the weighted means is a type of mean that is basically calculated by multiplying great probability that is associated with its associated outcome, and also then we try to summing all the products together. right? So for trimmed mean, it's a truncated mean, or I mean, we also call it as a truncated mean, is a statistical measure of a central tendency. Basically, it involves the calculation of the mean after discarding given parts of some probability distribution or a sample at the high or a low end, and especially typically discarded as equal amount of both. So this number of points that has to be discarded usually given as a percentage of the total number of points. But in fact, you may also give it as a fixed number of points. Okay, the correlations is a statistic that basically measures the degree which two variables move in relation to each other. Okay, and finally the regression lines. Okay, it's a straight line basically that describes how a response variable y changes as an explanatory variable x changes. So that's what this says. In fact, through regression lines, it can be used to predict the value of y for a given x, right? Now, if you try to consider a set of categorical data and also numerical data within an SIoT data set, okay, this table describes certain set of applications and services which has both categorical data and this numerical data. For example, let's say we have a location, set of services, and its IDs. The location is a service, ID 1. Similarly, date time is a service, and the ID 2. The point of interest, people's presence. So for each, a sequence of ID has been allocated so that you can straight away identify these services by using the service IDs. Okay, and further, if you look into the same set SIoT data set, there are certain applications like crash detect app, street light app, parking app, crowd app, driver monitoring app, fire detect app, irrigations app. Okay, and each app has been allocated an ID 1, 2, some IDs. So and each application has some services. Now, if you look into for example, crash detect app, the purpose of this app is basically it evaluates the car crash with environment and traffic sensors. What you can notice here is each applications has some services, and those services are basically generated through a sensors attached to that particular applications. For this crash detection applications, the environmental as well as traffic sensors are used. Similarly, for a street light, okay, so you have a light sensors that will be used, right? So depending on the presence of an object or a human, it starts brightening. Okay, and it provides. See, you can try to map between these two. See, for example, crash detect app has 5, 8, and 10 service. So the 5, 8, and 10 services are the environment and also the traffic status, okay, and movement. So if you observe within the bracket, right, the environment is using the carbon dioxide, the sound, the temperature, AC, actuators as a irrigator sensors are used in this case, and also under traffic status has been obtained. Okay, accelerometer as well as a gyroscope sensors are generating this data, right? So in this case, right, now this is the sample of a data set that has been provided or generated by using a swim model, right? And it's available. Okay. Similarly, now when we try to analyze or perform statistical analysis on these data, right? Now we have to understand what is the distribution of these data, how this data has been distributed, right? So to find that, right? So in SIoT, the environments are represented as a universe or a space, right? Where we are trying to perform some analysis, right? So, and now this analysis basically based on, right, the variables and uncertainty. So we don't know what exactly the data will be generated by a specific. We have a set of range, right? So for example, temperature could range from something like 25 to 40 degree or whatever the range that has been assigned to that. Okay. So, and since it is an IoT based applications, we have an uncertainty with respect to the data, right? So basically, the statistics focuses on the analysis of data, right? By experimental design or experimental understanding, and since you have an uncertainties, the statistics where which is a state of limited knowledge, where it is impossible to exactly describe the existing state or the future outcome, right? So it basically requires a context, like what type of data that has been generated, whether it is numerical or a character or a multimedia like a binary or an image audio, right? So to get the desired possible outcomes. Okay, so that's the reason we use the statistical analysis, right? And when it comes to the data distribution in a space, of course, it has a different dimensions, right? So some will be like 1D or 2D, or it could be three-dimensional data, right? Now, when I say 1D, of course, a point is a one-dimensional data, right? Or in a two-dimensional, we say length as well as the width. For example, for a three-dimensional, length, width, or depth, or in height, or a time, we can pass it as a parameter. For a four-dimensional, along with length, width, and depth, we can use time as a parameter. In fact, the 4D is also called as an astral plane. Okay, so or for a 3D, whenever we three-dimensional data, right? It's a position in a space-time, or we can also call it as an event, right? So when we, especially when it comes to the data set of an SIoT, it has both temporal correlations and also spatial correlations. An event which is in a spatio-temporal data set basically describes a spatial and also a temporal phenomenon that exists at a certain time t and also location x. So here we have a spatial locations and also spatial extensions like points, lines, or in areas. When it comes to spatial locations, we have a dynamic location, we have a fixed locations, right? So there are spatio-temporal events, right? Geo-referenced variables, geo-referenced time series, where certain, especially the dynamic locations, and Steven does not apply to this. There are certain moving points or the trajectories. So these are the possible things that can happen within the data set, right? And if you look into the properties of these data distributions, right? So any data distribution has properties like shape, central tendency, and also variability, right? So here where the shape or a center or a spread can be used, exploring the distribution with tables and graphs. So how do I find this distribution? How do I say that? What kind of distribution? You can explore this by using a tables or a graphs. The frequency distribution tables, or a bar chart, or a pie chart, or histograms, or by using a stem and leaf plots. So we can measure these things. To explore these, how the data has been distributed, you can use any of these methods. Okay, and if you look into the properties, right? And when we say the data distribution properties, it's basically measured in terms of shape, center, as well as variability, right? So when you try to measure it as a shape, okay, especially in a symmetrical distribution, where it is possible to draw a vertical line through the middle so that one side of the distribution is exact mirror image of an others, right? So for this, we can use kurtosis as a relative measure of the body and tail portions of the distributions. When it comes as a for a shape, when you try to measure through a shape. Similarly, measure of a central center, where we try to find the central tendency, which is a statistical measure basically that identifies a single score as a representative of an entire distribution. Okay, so for example, the central tendency are the mean, the medians, and the modes. Okay, and the measure of variability can be used, which basically provides a quantitative measure of the degree to which the scores in a distribution are spread out or clustered together. Okay? So whereas for a variability basically gives us the range, the interquartile range, and also the standard deviations. Okay, so what are the types of distribution, data distribution? So just to summarize, right? So distribution basically is a function that shows the possible values for a variables and how often they occur. Okay, so it is basically based on the simple inputs. So we have two kinds of types of distributions. One is continuous distribution and another is a discrete distribution, right? So under this you have a probability distribution. If you look into this, there are both discrete as well as continuous, right? So where we try to treat it as a function of x, right? And while calculating these distributions, of course, we use the basic terminology that has been used, like a mean, variance will be calculated. Okay, right? So now, what are the types of data that has data distribution, especially? Now, if you try to categorize this, a data, of course, one is discrete and another is continuous data. So under discrete, right, where we try to, if it is a discrete data, we try to estimate the outcomes and also the probabilities. If not, we try to find whether the data is symmetric or asymmetric. Okay, so if it is symmetric, the values are clustered around the central. Okay, again, when it is clustered around, if it is a binomial, or otherwise it's a uniform discrete. Now if the data is asymmetric, so the values are outliers, right? Only positives will be geometric, or again more positives you have negative binomial, and if it's more negative you go with hierogeometric, okay. So if it is discrete, these are the possible type of distribution that can happen. Whereas if it is continuous, right, the data is asymmetric or symmetric. So it falls into these two categories, either symmetric or asymmetric. Now, if it is asymmetric, obviously the values are outlier, and where we try to find whether only positives are there, more positive or more negative. If only positives, it may go to exponential, or more positives, it may go to log normal gamma or a Weibull distribution, or whenever it is a more negative, it can go to the minimum extreme, right? When it is, when the data is symmetric, right? So the values are clustered, of course, around the central, right? And you have two categories, like you either it could be uniform or likely values are outlier, right? So when it is outlier, either it could be a triangular or a normal or a logistic origin. Okay, so if you consider any data distribution that falls into these categories, looking into the type, okay, so we can say that, so these data can be in any of these forms. Now when it comes to uh, these types of distributions, of course there are different types, okay. So one or to showcase or just to show this, the discrete distribution example, like a binomial and a Poisson distribution looks like this, right? And other types of distributions are like you have I mean, for a continuous distribution you have a normal distribution, uniform distribution, Cauchy distribution, T distribution, chi-square distribution, F distribution, and exponential distribution, right? Weibull, right? So log normal distribution, right? So you can say this different set of distributions, right? Burbaum-Saunders distribution, gamma distribution, right? Double exponential distribution, and also power normal distributions, power log normal distribution, Turkey lambda distribution, extreme value type 1, beta distributions, right? So now for these distributions, okay, the probability of data distribution has to be calculated, let's say that. Now basically here we try to use the probability theory, which is an analysis of random phenomena built on the axioms, okay. So these probabilities related to the needs of a statistic, right? So, two types, one is conditional probability and independence probability. Of course, the condition probability, we go with a Bayesian approach to statistics, and then independent probability, independent observations to a likelihood functions, right? So when we say the probability distribution, so we have basically this Bayesian approach are basically used for statistics, okay, whereas the likelihood functions are based on the random variables. Again, it is for two types, like continuous random variables and discrete random variables. And that's what we try to say, that the densities will be calculated and the mass functions will be calculated. Now, to calculate the density functions, right? Like what exactly the density function are the basically functions that describe how the portion of data or likelihood of the portion of observations changes over the range of distribution. Okay, so two types of density functions are probability density functions and cumulative density function. That's what PDF and CDF. The probability density functions basically calculates the probability of an observing a given value, whereas the cumulative density function basically calculates the probability of an observation which is equal or less than a value. Okay, and the mass function, probability mass function, which is is the probability distribution of a discrete random variable, basically, and it provides the possible values and their associated probabilities, right? So to do this, uh, we try to perform the hypothesis testing of an data distribution. Okay. So what we do is we first establish the central issues like null and alternative hypothesis, type 1 and type 2 errors, or test statistics, and critical regions, and also significance and powers. The null hypothesis, H1, decision about the null hypothesis H0 will falls into two categories, either reject or fail to reject, or true or false. Okay, so if it is type 1, okay, type 1 error, if it is false positive, okay, we call that as an the alpha, right? So whereas if it is the correct, if it draws an correct inference and you have a true positive, 1 minus beta, right? And you have a correct inference and a true negative, of course, 1 minus alpha. And if for type 2 error, false negative, it's a beta decisions. Okay, so when you start thinking about these things, what from a statistical modeling perspective, so basically the statistical models incorporate distinct variables that are practiced for interpreting connections with various sorts of variables, especially in statistical models or specific techniques such as like we use hypothesis testing, confidence intervals, etc., to make inside that validate defined conditions or an hypothesis. If we take an example in regression analysis, a various number of variables are used to identify the impact of an explanatory variable on the independent variables. From sampling, the probability spaces as assumptions to diagnostic approaches are used to make an inferences. So apparently, over a specific set of data, the statistical models are utilized to identify interferences on a relatively small set of data for understanding the nature of underlying data. The same data, whereas if you try to compare this with a machine learning perspective, is basically used to make predictions, and its explanatory performance can be evaluated by knowing how generalized it is across a new amount of data which has not been fed before. Okay, and also the it's a process of cross validation is conducted in order to check the data probability, that makes sure that ML model does not overfit or an underfit to the provided amount of data. And also in ML, the data is cleaned, regulated in a way that it can be understood by the machine easily, and no nominal statistic can proceed into this process. There are, of course, various types of techniques in machine learning to make predictions, like you have classification, regression, clustering, etc. Right? So, in fact, in ML models, error measures like RMSE, MSE, etc., can be deployed for regression, and true positive and false positive can be used for classification problems. Now, with this basics things, okay, again, I'll try to cover up certain testing things while demonstrating the codes, like especially for an hypothesis testing, right? Now, I'll just move on to the ontology model, or the necessity of an ontology model for an SIoT as well as industrial data. Now, what is an ontology? It says a specification of a conceptualization, right? It basically has a representation, a formal naming, a definition of the categories, the properties and relations between the concepts, data and entities that substantiate one or many or all domains of discourse, right? Basically, ontology is a way of showing the properties of a subject area and how they are related. Okay, so it means when multiple sensors are connected and these sensors are generating a data and we are developing some applications by using IIoT or for an SIoT, how these devices are related. In a simplest way, I can say that it is similar to an ER diagram that we use for a database management system. Okay, so where we try to identify the set of attributes, and also like whether it is an atomic, it has an atomic value or not, or a composite attribute, the type of attribute it has. Okay, and also the relationship between the entities, right? Similarly, in the same manner that the ontologies, we try to use all this and try to establish the relations between the devices. Okay, so we can define the ontology as a set of concepts or the categories and the relations that represent the subject. It is basically based on the concept or the context that we are trying to represent. So ontology specifies the conceptualization between different instances in the context of knowledge sharing. Now, before in SIoT, if you look into the architecture, at the component layer, we have ID, we have trust management, service discovery, service compositions, owner control, and all, right? Now, when we say these things, especially the trust management, I mean the relationship management and trust management, basically defines us what are the data that has to be shared between the devices. Suppose if device A is in parent object relationship with another object, it is restricting certain informations which cannot be exchanged between these devices. Similarly, if the devices are in co-work relationship, it cannot share the personal information of a devices. Rather, it can share only the official information where these devices are trying to achieve a common goal. Okay, so ontological model will helps us to conceptualize these things and find the instances, and it helps us to knowledge sharing. Okay, basically an ontology is a description, so it's like a formal specification of a program, right? Like we say that what is the input, what is the processing logic, and what will be the output, right? So the ontology basically describes the concepts, the relationship that can exist for an agent or in a community of. Okay, so when the knowledge of a domain is represented in a declarative formalism, the set of objects that can be used to represent, we call it as an universe of discourse, right? So this set of objects and also the describable relationships among them, are reflected in the representational vocabulary, which is a knowledge-based program that represents the knowledge. Okay, so in fact, most of the ontologies, describes the individuals. Now here, the individuals are the instances, the classes are the concepts. Okay, like the attributes and also relations, right? So it basically describes the instances, the classes, the attributes, and also the relations. Now when we say the individuals, individuals are the instances of an object. It means at the ground level. What are these ground level? The type of sensor that has been used. Let's say temperature sensor has been used. Now temperature is generating some temperature sensor is generating some temperature value. Okay, so ground level, these individuals are the objects. Classes are the sets or collections or the concepts like similar in a programming or set of things. For example, I try to create an environment where that environment include some few applications, and each applications has certain sensors connected to it which are generating the values for that. Okay. And third one is the attributes, right? So attributes are the aspects or the properties or the features or the set of characteristics, parameters that these objects has or the classes have. Okay. And the relations is a way in which the classes and the individuals that can be related to one another. So we can say that classes are the entities and individuals are individual attributes when we try to relate this with the ER diagram. Okay. And the function terms are the complex structures that are formed from certain relations that can be used in place of an individual term in a statement. Okay. And the restrictions has a formally we can state stated descriptions of what must be the true in order for some assertion that has to be accepted as an input, you know. Okay. And there are certain set of rules and axioms that has axioms and events that has to be defined when we start designing an ontological model. Basically, the rules are the statements in the form of an if and then sentence, basically, that describes the logical inferences which can be drawn from an assertion in a particular form. Okay. Whereas the axioms are the assertions like that includes the rules in a logical form. Okay. That together compromises the overall theory that the ontology describes in its domain of an application, whereas the events that basically changes or changing of attributes or relations, you know. So why do we now if you look into this, why do we need an ontology? Okay, we need an ontology to discover whether the data has any inconsistencies, which is also known as validation. Now, in an SIoT or an IIoT, the data are generated, okay, and we have to know that how this data can be utilized. Okay, so to know that, we have to check the validity of the data, whether the data is consistent or has an inconsistent. To and also to extract the implicit information from the data, which is known as inferences, right? So, as an example, if you take of a validation, so if you consider a glitch in the data whereby a person was incorrectly named as the parent of themselves, okay, so sometimes it happens, right? Now, especially in an SIoT, since it is a relationship based interactions or the data exchange that happens or the communication that happens based on the relationship and also the user behavior, if you incorrectly name that person or the user, it automatically changes the relationship between the devices. Okay, so that's the reason we need to have an ontological model. So in adding the data to the ontological model, we would spot that a person entity was attempting to take both the relationship. Okay, so see, as discussed in my previous session, you know, we started trying to understand the relationship. You know, for example, a device D1 with D2 can have only one relationship at a time. Okay. Now, once we start writing an ontological model, we can identify that whether the same entity or the same individuals, right, may have two relationships with the same device. Okay, so that can be easily identified, right? So ontological model will help us to identify those inconsistencies, right? So basically these ontologies are conceptualizations that the terms in the vocabulary are planned to capture. Okay, and also sometimes these ontologies can be referred as describing some domain of knowledge. When we say domain of knowledge, there are two types of ontology specification in a knowledge system. One is domain factual knowledge, another is problem solving knowledge. The domain factual knowledge provides the knowledge about the objective realities in the domain of interest. Whereas problem solving knowledge provides us the knowledge about how to achieve various goals. Now, while designing an ontological model, we try to find what is the domain of interest. If in that case, we go with the domain factual knowledge. Okay. The ontological analysis explains the structure of a knowledge, which is more essential part for any system in the representation of a domain. Especially the first step to develop a knowledge representation system and a vocabulary, and secondly is to perform an ontological analysis of the field. Okay, so in an if you look into the SIoT based real world aspects, okay, it has divided into three different layers, right? The physical layer, the information layer, and also the function layer. Physical layer are a set of objects or the things, right? Where you have a sensors, actuators. Whereas the information layer are the data and also the metadata about the knowledge provided by the things. And also it contains the social relationship among the things. If you look into the SIoT perspective, I mean, when you try to use an SIoT, the SIoT has these things. And finally, the function layer has the set of services that are provided by these things. Okay. Now, ontological analysis basically helps us to explain the structure of knowledge, which is more essential part, right, to represent this, right? So, in fact, these functional layers, right, or these ontological model will help us to correlate between all these three layers of an social internet of things, right? So if I take an example of a smart city, right? So any ontology model, so generally the ontology model looks like this. Okay, so if I take an this is an example of a smart city, right? So I mean under social IoT, where you have a set of applications that are connected to a smart city, like street light app, traffic app, bus app, smartphone detection app, parking app, crowd app, uh, drive monitoring app, city consumption app, street light app. Okay, now further, if you take an example of city consumption app, it basically uses an energy consumption as an individual. Whereas if you take an example of street light app, it checks the people's presence, the traffic status, the street light. So what we are trying here is, when we try to build an model, ontological model, we try to identify the set of sensors connected to the applications, or these sensors are providing some services to these applications, and the applications are within an environment. Okay, right? So this particular ontological model helps us to find the the relation, and in fact the set of devices that are connected, right? The set of sensors that are connected to a specific applications, right? Now, under this, when we say different ontologies, there are basically three different types of ontological model. One is the device ontology, then physical domain ontology, and estimation ontology, right? So three different types of ontology, right? Now, what exactly this device ontology, right? Excuse me. The device ontology models are basically the actual hardware devices that may exist in the network. So what we are trying in ontological model is, it's like building a specification. How many devices are connected to this particular application? For example, I am trying to build a smart city application. What are as a smart city as an environment, right? Now, what are the applications that can involve inside this are decided based on these things, right? Like you have a different set of applications. And what are the devices that are connected to these applications are decided based on device ontology. It means it covers all the hardware devices that may exist in the network. So for our middleware, it can be regarded as the device description repository that can be accessed for discovery through the social aspect based on the relationship between the devices. Okay, so of course, in the middleware we try to find or we perform service discovery and service compositions. Now, to find that services, which particular device is providing that services, right? The device ontology will help us to do that. Okay, so the device ontology is accessed to identify what things should be looked to satisfy an application's requirement. Suppose I want to build some, let's say, a restaurant app itself. Restaurant is an application. Now, what are the services that can be provided by this? Now, what are the hardwares required for this? Of course, I am trying to look for a best restaurant around me, and also I want to book the table of that particular restaurant. So when I say I want to book that particular table, means even that particular restaurant is using SIoT. Let's say that. Okay. So in that case, the set of sensors that are, see, to check whether the table is empty or full, we need a sensor. Similarly, the quality, whatever, to reach that particular restaurant, we need an environment sensors. Like what is the traffic status towards the path of that particular location. Okay. Now, how exact and also to locate that, we need a location, just the GPS. Okay, so ontological model, right, will help us to, especially the device ontology is basically focuses on the set of hardwares that are required for this. Okay, so what which device is providing what type of services is defined by using a device ontology. Okay, so the device ontology is access to identify what things should be looked up to satisfy an application requirement. In fact, to elaborate on the ontology, we consider that the IoT devices can be divided into 4 different types of classes. One is sensors, actuators, processor, and also the composite. Right? Basically, a sensor is a device that has the capability to measure a physical property of a real world, right? And actuator are the devices that has the capability to perform an operation or a control a system, physical entity in the real world. And the processor is a device that is capable of to perform the computation operations on the data. And composite device consists of at least any two of the devices that has been here. Either it could be sensors or an actuators, or it could be an processor, right? Now, when we try to consider that, let's say, if you consider that an application built on the top of a SIoT middleware, right? Obviously, it should include the network, the device agnostic, and also the social relationship among the each devices that are connected. Okay. So in fact, to elaborate the ontology with respect to the social IoT, basically what we do is we try to consider the relationship between the users and object. If you look into the different types of relationship, the basic categories are two types, right? User to object, object to object, right? Now, when we say that there are certain devices that are involved in this, we generally consider the to perform an object profiling. Okay, so we use user and object relationship. Of course, it can be further extended for the object to object relationship also, right? Now, when we say, now, how do I build a device ontology for a smart city applications? Okay, so this particular diagram, shows us how the device ontology model can be used for a social IoT relationship. Okay. Now, this application, okay, this is a smart city, right? And smart city has a relationship with a set of relations here, like sibling object relationship, co-location object relationship, guest object relationship, and also service object relationship. Okay, so if you observe this, there are set of relationship that are already available, and these relationships have been imposed to the smart city applications, right? And we try to divide or represent this as a virtual object, composite virtual object, and also microservices. These microservices are the set of sensors, right? For if you look into this, there is a traffic app. Traffic app has a location, it has an environment, it has a traffic status, and also the movement. Right? Now, all this, the location, the environment, the traffic status, and also movement are providing a microservices to this particular traffic app. And also, if you consider this drive monitoring, right? The drive monitoring. Drive monitoring has an environment, it has a weather, and also traffic status, and also street light and movement. Okay. Now, how this particular weather is related to this geolocation, right? So there is an object, right? So there is a set of objects which are basically we represent the smart city as a virtual object, okay, and the composite or the class, right, class of an virtual objects, right, and the set of services provided by these objects. Now, here, if you observe, this weather is in relationship with geolocation. It has a is in relationship with geolocation, and also environment has an some some object, and here also this environment has some object. Similarly, this location is currently in some location, right? And also the movement is an attribute, right? Or an individual has a social friend. Now we try to create certain virtual objects here, like service as an virtual object. Some intermediate object that is trying to access objects, services, social friend, identification, right? So we create these intermediate relationships. Okay, ontological model will help us to identify these things. You know, the traffic status identifies, right? So it has an identification. Similarly, this traffic status will also has an identification. Similarly, street light has some service. Okay, and movement is has a social friend relationship. And this environment has some object, right? So what we try is, we first identify the set of device sensors or an actuators or a set of sensors, and we try to relate this by establishing a relationship between them. It's not only the social relationship. First, at the first level, at the ground level, we try to add a new relation to this, which has what type of relation? This environment has some object and it has some identification. It has some social friend. It has some services, right? So from this, we can convert this into a social IoT, where we say that this environment has a sibling object relationship. Since it has a both as a same object. Similarly, whether is in
स्लाइड बना रहा हूँ सर, तो सर पहली बार बना रहा हूँ, समझ में नहीं आ रहा कहाँ से मारूं.
So this whether is in co-location object relationship, because it basically both are saying that it is in some current relation. Similarly, the traffic status is in co-location object relationship. So what we are trying here is the set of attributes, or the set of services or the set of devices that are connected within a smart city, right? We are trying to group or cluster them based on the social relationship to this. So ontology model is helping us for for an SIoT based applications here, right? To cluster them or to group them. How many or what are the devices that are involved in co-location object relationship, or what are the objects that are in social service object relationship, or the set of devices that are in sibling object relationship. Okay, so this is with respect to device. So device ontology basically focuses on the hardwares. Okay, right? Then second type is the physical domain ontology. Right? Basically this domain ontology is a type of ontology which describes all the relevant concepts and the relationship among the devices in a single domain of interest. Okay. When we say single domain of interest, so the set of devices involved in this. So this is created with two main goals. One is to create a model of a real world entities like physical concept. So any IoT middleware can extract this information or the knowledge about the real world, which is the common task that has to be performed within the internet, right? And the second is to model mathematical formulas and also the functions, as they are basically the first alternative that has to be utilized when no device can provide this needed service, right? So this domain ontology, there are different classes. Okay, so one is the physical concept. Right? It's a real world object or the property that can be measured, whereas the physical unit is the output unit of a real world property measurement. The mathematical data type involves a set of numbers that can represent a real world property measurement, and the formulas can be mathematical expressions that computes a numerical value representing the real world property, and the functions where the formulas are implemented by using the functions that defines the required input and output machine data types, right? So if you look into the main classes of a domain ontology, you know, it includes a particular domain, where each device to find out the relationship. Okay, especially for an SIoT based applications, relationship will be used as an metric to find out the devices that are providing a set of services, right? And here in a physical domain ontology for an SIoT based applications, right? So it includes a domain where each devices tries to find out the relationship. So among the different devices in a given middleware, it tries to connect the relations among each services that are provided in it. So first, you try to identify the devices, and then you try to find the services provided by each device. Okay, so it consists both a common concept with a specific domains in it, right? So according to the particular domain, okay, we try to capture this social relationship among the different devices, right? How these devices are related. Okay, we try to find what are the relationships, the social relationship that you have between those devices based on the set of services that are provided by these devices. Okay, right? Now for a domain ontology, for a domain ontology, okay, basically it based on the SIoT relations. Okay, now of course we try to extend the same diagram, okay, the smart city applications, where we concentrated more on the hardwares in a device ontology. Here the set of services that has been provided based on by these devices, and we try to establish the relationship among them based on the services that are provided by each individuals within a specific applications, right? So if you observe this, within a smart city you have a three different applications. One is street light app, parking app, and bus app. Okay, now of course street light app is checking the people's presence. The parking app is checking the locations, right? And the same location has been utilized by the bus app, where it is trying to encounter count the number of people, right? And it has a date and time, the movement, okay, right? So again the date and time will be identified, which has an identification relationship. Now whether it has the movement has a service or not, or we try to check in this street light app as a street light, it checks whether it has another object or not, and also if so it has an object. Okay, and the traffic app is in some location, so that is provided by in which current location, right? So finally if you observe, people presence has number of people, the final outcome is the number. Traffic status is giving you some location, and finally the outcome is the location. Similarly, the movement is providing some service, the outcome is some service. Okay, and also the people counter, right? It will give us a list of social friends. Again, the location is giving us. See, finally, from an hardware, right? So we are trying to provide a set of services in domain ontology specific to some applications, right? We try to find the relationship among the devices, and those devices are how they are connected, right? What type of social relationship it has. So based on that, the location is in co-location object relationship, the date time is in co-location object. Similarly, the traffic status has a guardian object relationship. Street light has a sibling object relationship. The people counter has a social object relationship. The movement has a service object relationship. Again, the people presence has a co-work relationship. And these relationships are further found or identified or established along with the minimal relationship, that minimal constraint that you have on this, or the basic relationship constraints, like to decide whether it is a co-location or not. So we say that the devices must be located in a same or within a range of a set of people involved in this, or the who are working for a common goal or sharing common data, right? So similarly, parent object or a sibling object relationship or a social object relationship. Here we try to, depending on the hardwares that are providing these services, we try to establish a relationship among the devices. Okay, under physical domain ontology. Okay, and the third one is the estimation ontology. So here, this is an in fact most unusual ontological model, right? This is basically in charge of storing different mathematical models that make up the entire toolbox that will be carried out by the expert system designers in the field of like robotics or estimation, sensor networking, etc. So instead of simply storing these models, the estimation ontology must also organize them in a way that makes them machine accessible. So finally, our middleware should be able to find which models that are appropriate for a given situation and which model has some sense or which is an optimal, right? So it's not just storing the data, rather we have to access those data and find which is applicable for us, right? So the estimation ontology must provide a well-designed set of attributes for each model. So, and also as an intricate social relationship between the models, devices, and also the physical concept. The estimation and prediction models includes are basically used during the automated estimation process, as well as well before looking up the phase in the probabilistic discovery. So, for example, the Kalman filter, where each component in its matrices and the vectors are functions of physical concepts from a domain ontology. So, for an instance, if you take an input vector for a user target location, that could be defined as a triplet of 3D acceleration or a velocity or a 3D positions, right? So the association and correlation models are used in estimation theory, okay, which basically describes the numerous conditional probability relationship, okay, related to one physical phenomenon as a function of another. So, for example, if you take an instance, the probability of value of a temperature sensor given the value of a daylight sensor. Okay. So, in addition, these models can be used to solve the association problem that may occur, for instance, in a multiple target tracking. Okay. So, and also the some error models, where these models basically describes the different ways that uncertainties can be introduced into the measurements and actuations. Okay. These are generally represented as a process of stochastic model, right? In a simple additive Gaussian noise model, right? So estimation ontology basically helps us to find, to understand the uncertainties of the data, right? So if you try to build an estimation ontology to this, you know, uh, it is similar to the physical domain ontology, okay, but what we, this is more of comes under the middleware, where how do we find, or how do we estimate these uh, data, or the how do we discover these data, and which model. Say, for example, now I want to represent, in fact, I have represented location, date, time, point of event, people's presence, right? Now, through this, within a smart city applications, let's say I want to find the number of people present in a specific locations, right? And also, I must be able to track those people, and also, or I can track the point of interest that has happened in a specific event. Or let's say I want to apply some prediction algorithm, you know, for a crowd app. Let's say for a weather-based weather applications, right? So we have, let's say, weather has been connected to this, right? So we use these estimation ontology models to predict basically. In fact, a lot of work can be done in estimation ontology. Specifically, we don't have a exact model. Rather, depending on the distribution of these data, depending on the variety of data that has been generated, or the variability of the data that has been generated by these sensors, we try to find which type of model that can be applicable to this, right? So when we, especially in an SIoT or an IIoT, right, we try to focus on a specific application. Now, when we say that you have a specific application, now that application involves certain sensors, actuators, and these devices are generating some data. When these devices are generating some data, we have to draw or infer some knowledge out of that, and that knowledge helps us to take some action. Now, suppose I want to predict what will be the weather for the next 3 days, right? So we'll use this estimation ontology model for that. Okay, so where we try to find the basically find the uncertainties in the within the data, okay, and based on those data, we try to find the solutions for that, find the related models, right? And we try whether it is a discrete, it is generating a discrete data or a continuous data, or should I go with any stochastic process, right? Like Markov chain model, I mean Markov models or not, right? So that depends on an individual applications, okay, right? So when it comes to industrial IoT, right? So of course, industrial IoT has a different set of applications like robotics, medical devices, software-defined production process, and it involves set of devices like sensors, actuators, RFIDs, smartphones, right? And as a set of systems like power distribution, security, health, and agriculture. And these IoTs are used in different applications. In fact, like robotics, medical devices, traffic monitoring, smart grid building, automations, okay, and also e-health, right? So, in fact, there are many companies are utilizing this IoT, you know, like in IBM, a fully managed cloud hosted services with the capabilities for device registrations, the connectivity, the control, rapid visualization, and data storage. Right. So we can make use of IBM cloud also, and similarly, the Microsoft Azure, right? So Azure IoT is a collection of managed and platform services across the edge of cloud, basically that connects, that monitors, different set. Okay, right? Uh, it also includes the security, right? And different operating system for the devices and the equipment, which can be used for data analytics, that helps business to build, so where the certain prediction models will be used. In fact, Microsoft Azure provides us an IoT platform where anyone can register and start work on that, and also various data that will be generated by an IoT. So, like different devices. One best example is like the vehicle automation, right? So, and also construction telematics, where certain devices like equipments, the tracking, the trucks that are equipped with sensors, geotagging sensors, right? Which helps us to monitor those trucks, right? The benefit of IoT when we try to use it in an industries are like higher process transparencies, like and also lower maintenance costs. It reduces the machine downtime, right? So when we say you have a set of you are applying these statistical method or models or an ontological model for an SIoT and IIoT, both generates a huge amount of data, right? And these data are heterogeneous, generated by heterogeneous devices. Okay, so we try to perform certain testing on these data. One best testing is the hypothesis, and then we do perform a data analysis. Basically, there are two types of hypothesis testing. Say, in fact, I have made it as a demo part. Of course, I'll be executing these codes, right? And before executing the codes, I'm just trying to present the basics of these things. Hypothesis testing, basically, we use it for a null hypothesis, which is an initial assumption about an event, where they say that it's a ground truth, the measurement of a ground truth, or you can refer it as a ground truth. And also you have an alternate hypothesis, which is an assumption that encounters the initial, that counters the initial assumptions. So we have H0 and H1, the null hypothesis, which can be represented as H0 hypothesis, and the alternate hypothesis or counter hypothesis assumptions as an H1 hypothesis, right? Now, Second thing is the likelihood of the following events that has been happening. That depends on the ground truth, right? If the H0 is true, then we accept that H0. If the H0 is not true, obviously, so we'll try to reject, and the alternate, the H1 is accepted. Whereas the remaining possibilities can be outlined as you have null hypothesis is true, but we reject it. Sometimes the null hypothesis is not true, but we did not reject it. Like we try to accept it also. So since we have not recognized the right hypothesis, we may fall into the type 1 error or type 2 error. So when we say type 1 error basically occurs when we reject the null hypothesis, even though it was a true. Okay. Whereas type 2 error, it was accepting the null hypothesis, even though it was a wrong. Okay, right? So to find the confidence of a null hypothesis, right? A probability p-value basically explains us the likelihood of an assumptions that is being true based on the null hypothesis. It means to accept or reject our null hypothesis is after determining our p-value. Now, p-value helps us to determine the null hypothesis, right, which has been accepted or rejected. Okay, so p-value is usually within the range of 0 and 1. The probability of making a good choice, so the p-value will help us to do this. And there is a alpha value. Alpha level allows us to ascertain whether to consider accepting or rejecting the null hypothesis. So generally we calculate these two values, p-value and alpha values. Alpha value allows us to whether to decide whether to consider accepting or rejecting the null hypothesis. Generally, the probability here is of making a bad choice. Okay, right? So to obtain the confidence value, okay, the confidence level, if the confidence level from what we have seen from our data is something around 95%, then the alpha will be 0.05. So alpha can be calculated as 1 minus confidence level. So 0.05, right? And the statistical technique for hypothesis testings are basically three popular tests are there. One is chi-square test, t-test, and ANOVA test, right? So the chi-square test is adopted when there is a need to analyze two categorical elements in a data set. Okay, so it focuses on the relationship between these two categorical variables. So which is it's a tool used when checking how divergent the observed frequency is from the expected results. In chi-square test, the null hypothesis, when two variables like A and B are not dependent and have no relationship between them. The alternate hypothesis is if variable A depends on variable B or vice versa. So we try to find the dependency of between two variables, right? So the equation, the formula used here is the summation of the observed minus expected square by expected outcome. Okay. So for t-test is utilized when we plan to evaluate the discrepancy between the means of two groups of samples. I have a set of two groups. I try to find evaluate the discrepancy. Then we can go with the t-test, right? So t-test is used for a continuous variables, right? So it has of three basic types: one sample t-test, two sample t-test, and a paired t-test. Okay. So it checks in a one sample t-test. It checks whether the population has a different mean from the sample. In a two sample t-test, it checks juxtaposes the means of two groups that are not dependent on each other and compares the population means to ascertain if there is a huge difference. And paired t-test is used in checking and comparing the means of different samples from a group, right? So the one sample t-test can be calculated as a minus bx by n, where the observed mean group is A, assumption population means is B, the standard deviation of the data group is X, and the number of observation in the group is N, right? And to calculate the two sample t-test, right? MA minus MB star and NA plus V and B, where data sample A is a mean in MA, data sample B's mean is MB, the size of sample A is NA, and the size of sample B is NB, and the variable is V, right? Okay. So similarly, the variable the pair t-test is calculated. And also the ANOVA tests are used where ANOVA is a word that is coined from analysis of variance, right? So it's a statistical concept that shows the difference between means of more than two independent groups by using variance analysis on samples from those groups, right? So it is used for checking the contrast between three or more samples with one test. The categorical classes has over two categories. It understands how each of them connects to your dependent variable, right? So when we talk about these things, the data analysis, it is a cleaning, data cleaning is a process of finding and correcting the inaccurate or incorrect data that are present in the data set, right? So there are different methods to handle this: deleting the columns with missing data, or deleting the whole rows with missing data, or filling the missing data with a value, where we call it as an imputation, or imputation with an additional column, filling with a regression model, right? Okay. So, and also we try to use the normal Gaussian distribution, right? So it's in the probability theory is it's a type of continuous probability distribution for a real valued random variables, right? So generally it's a bell-shaped curve, right? So which lies around the mean, right? The mean, median, and mode of Gaussian distribution are of same, right? And other various methods to analyze distributions are histogram, QQ plots, KD plots, and skewness and kurtosis, right? So this histogram is a graphical representation that organizes a group of data points into a user-specific ranges. Whereas the QQ plot is a plot of quantiles of the first data set against the quantiles of a second data set. And KD plot is a kernel distribution estimation plot, which depicts the probability density function of a continuous or a non-parametric data variables. That is, we can plot for a univariant or a multiple variable altogether. And the skewness and kurtosis, the skewness is a measure of an symmetry, or more precisely, it's a lack of symmetry, right? A distribution or a data set is a symmetric if it looks the same to the left and the right of the center point, right? Kurtosis is a measure of whether the data are heavily tailed or light tailed related to a normal distribution, right? So with this background, okay, I'll move on to the demonstration of this. Okay. Okay. So here we try to find the missing values, you know. So, right? Yeah. I'll just choose the file. Okay. Now this is the sample data set that has been used, right? Okay. Okay. Let me to know this whether the data is missing the okay, whether the data has missing values or not, you know. Okay, so you can see this these data you have a non-null values. Okay, this data. So here you can see this no data are missing in this case, right? Okay. Okay. And also to count like how to know whether the data has a missing values or not. Again, in this case, you don't have any data, right? Right? Okay. Just a minute. Just a minute. Okay. So another way of handling missing values like is null, not null, drop null, fill null, replace, interpolate. So right. So we can use all these methods, right, to check the values, right. So this now here you can see this. We are just checking is null, right. So it displays the first score, the second score, and also the third score, right? So again, here displays the not null, right? Fill, see, you can see this filling the values by using the key,
open
we try to fill the missing value. With padding here, right? So interpolating
Please, participants, mute your mic.
so with a linear method and also the direction as a forward direction, right? So this is to fill the missing values. Similarly, I have hypothesis testing. We are just trying to check whether it has a null value, right? Depending on here you can see this. We are trying to display the top 5 values, right? And also the header by using this, and also the 10 samples are displayed, okay? And checking whether it has a null value or not, right? And also whether it is unique or not, okay? And also we are trying to describe whether it is basically on based on the device brand. We are trying to calculate the mean, standard deviation, minima, right? All these things, right? And also with respect to the distance, right? And calculating the percentile with respect to distance, and calculating the same percentile with respect to device brand, okay? Now here we are trying to calculate the degree of freedom, the p-value, right? And the stat values, right? So that's the reason I gave you the basic about that, right? The p values, the usage of p values, right? And also the alphas, right? So basically the p values are basically it explains the likelihood of an assumption that is being true based on the null hypothesis, right? Okay, so it will allow us to accept or reject, right? So that right. So here the degree of freedom is 112, right? And so for our sample, that's the reason I said the alpha value is something around 0.05, right? I mean the confidence, right? Okay. So here, this basically helps that whether to reject the null hypothesis or accept the null hypothesis can be found, you know. In this case, we try to reject the null hypothesis based on the H0 value. Similarly, we try to go with the t-test, right? The t-test is performed for one sample and also the 2 samples. For an one sample, right? So the value resulted with a statistics p-value thus, and also for 2 samples based on the classes, you know. We try to check the ratio, which has resulted in this 1.48. Okay, and finally we can go with an ANOVA test, right? One way and two way. Sorry, one way, right? So it has resulted in some value, right? So finally, to summarize all these things, okay, so you know, if you try to display all the based on this the t-test results, the p-values, again for the classes, the sum square, the different, the df, f, right, and the pr, right? So we can categorize these classes, whether it belongs to class 1, class 2, and the ratio of 2 classes can be observed in this. Okay, and with respect to the distribution, how the data has been distributed. So to look into the data distributions, right? So this is the data set that has been used. Okay, to check the skewness within the data, right? So with respect to distance as an attribute, connection type as an attribute, protocol, device type, and device brand, you know. So and also certain distribution can be checked by using histogram, right? So basically, I told you that histogram is a graphical representation where we try to group of different data points within a user specific range, right? So you can see this again, distribution of some variables using with respect to connection type, right? With respect to distance, how the data has been distributed with respect to protocol and connection type, okay, right? So these are the by using a histogram, basically, no? Right? So and also by using KDE plot, and I told you that KDE plot basically it's a estimation plot which depicts the probability density function of a continuous or a non-parametric data variable, right? So you can observe this that for a different set of attributes, what is the density based on the device brand it has been used in, right? Similarly, based on a device brand, again the density, right? Cumulative, right? And and also by using the stats, right? So here, by using a stat, we are trying to display plot the probability between the theoretical quartile and also the ordered values, right? Okay. So in fact, uh, most of the statistics models, right? So the building blocks can be considered like mean, median, mode, SD, variance, right? Interquartile, discriminate, right? So all these things can be used in our experiment. I mean, here we have used the social IoT data set where device protocol, distance, device brand, connection types are used. Okay, right? So yeah. So to conclude this, you know, in this particular session, I try to give some insights on the statistical, so the fundamental statistics, and also the models. Hello.
Sir?
I'm sorry, I lost network connection actually. Can you
Okay.
able to hear me now?
Yes, sir. We can able to hear you, sir.
Yeah. This, I mean, I was about to conclude this, right? So I tried to focus on providing, giving some insights on statistical data and also the types of ontological model that can be used to represent the SIoT data as well as the IIoT data, and the basic functions or the statistical method way of analyzing the data, and try to present or demo that through the code. Okay, so thank you for patience listening. So let me open for some queries.